Right now, somewhere in this galaxy, another civilization might be staring at the stars and wondering the exact same thing you are. The mathematics say they should exist. Hundreds of billions of potentially habitable worlds orbit hundreds of billions of stars in our galaxy alone, and there are 2 trillion galaxies beyond ours. The numbers practically demand that intelligent life has emerged countless times across cosmic history. Yet here is the part that should unsettle you. The universe was not built for meetings. The same physical laws that allow stars to burn and planets to form have constructed a prison of distance, energy, time, and expansion so absolute that 2 civilizations may never touch, never meet, never confirm each other's existence through anything but silence. This is not speculation, this is physics. If you enjoy journeys that permanently change how you see reality, consider tapping that like button and subscribing. Now, get yourself comfortable. Let's begin. Start with a number that should fill you with hope. 400 billion. That is a conservative estimate for how many stars burn inside our galaxy right now. 400 billion nuclear furnaces converting hydrogen into helium, pouring light and heat into the void, warming whatever worlds happen to orbit nearby. Some of those stars are ancient red dwarfs that ignited before Earth existed and will still be burning trillions of years after our sun goes dark. Others are young blue supergiants, luminous and reckless, destined to exhaust themselves in a few million years. Most fall somewhere between these extremes, ordinary stars living ordinary stellar lives for billions of years. And around those ordinary stars orbit ordinary planets where the ordinary laws of chemistry have had billions of years to do extraordinary things. We know planets are common because we have counted them. The Kepler Space Telescope, launched in 2009, stared at a single patch of sky in the constellation Cygnus for 4 consecutive years, monitoring the brightness of over 150,000 stars. It was watching for dips, tiny decreases in starlight caused by a planet passing between its star and the telescope. Those dips are subtle. An Earth-sized planet crossing a Sun-sized star blocks roughly 1/100% of the star's light. Detecting that signal requires instruments of extraordinary precision and patience measured in years. Kepler found thousands of planets. Not dozens, not hundreds, thousands. Rocky worlds smaller than Earth. Gas giants larger than Jupiter. Planets orbiting so close to their stars that their surfaces glow with molten rock. Planets orbiting so far out that their atmospheres freeze into crystal shells. Planets in systems with 2 suns, 3 suns, planets orbiting dead stellar remnants, planets in configurations no theorist had predicted. When scientists extrapolated Kepler's findings across the full stellar population of the Milky Way, the conclusion was staggering. On average, every star in our galaxy hosts at least 1 planet. Many host several. Some harbour entire planetary systems as architecturally complex as our own. The total planetary population of our galaxy likely exceeds 1 trillion individual worlds. 1 trillion. If you could visit 1 planet per second without pausing to sleep or breathe, the tour would take more than 31,000 years. Not all of those worlds can support life as we understand it. Many orbit too close to their parent stars, baking under radiation fierce enough to strip atmospheres and boil oceans into vapor. Others drift through the frozen outer reaches of their systems, where temperatures plunge hundreds of degrees below zero, and any surface water would be locked in ice kilometers thick. Gas giants like Jupiter and Saturn lack solid surfaces entirely, their atmospheres descending into crushing pressures where no recognizable biology could function. The universe builds planets with astonishing generosity, but most of those planets are hostile to the kind of chemistry that produces living things. Between these extremes, however, lies a region astronomers call the habitable zone. This is the band of orbital distances where conditions might allow liquid water to persist on a planet's surface. Not too close, where water boils. Not too far, where water freezes. The habitable zone shifts depending on the star. Around a dim red dwarf, it hugs close. Around a luminous blue star, it stretches outward. Around a star like our Sun, it falls in a range that includes Earth's orbit, a reassuring coincidence that reminds us our own existence is consistent with the rules we are describing. Liquid water is not a guarantee of life, but it is the only solvent in which every known biochemical process operates. Proteins fold in water, DNA replicates in water, cell membranes organize in water, amino acids assemble into functional chains in water. Every organism on Earth, from deep-sea thermophiles to alpine lichens, depends on liquid water at the molecular level. Where liquid water endures for billions of years, chemistry has the time and the medium to experiment its way toward complexity. Given enough time, enough raw materials, and enough liquid water, the molecular machinery of life appears to be a plausible. Conservative estimates suggest that roughly 20% of Sun-like stars host at least one rocky planet within their habitable zone. The Milky Way contains somewhere between 10 and 20 billion Sun-like stars. That yields between 2 and 4 billion potentially habitable worlds orbiting stars similar to our own. But Sun-like stars represent only a small slice of the galactic population. Red dwarfs, which make up approximately 70% of all stars in the galaxy, also host rocky planets in their habitable zones. The TRAPPIST-1 system, a red dwarf 40 light-years from Earth, hosts 7 rocky planets, 3 of which orbit within the habitable zone. When red dwarf systems are included, the total number of potentially habitable worlds in our galaxy climbs toward 10 billion or higher. 10 billion worlds where liquid water might flow. 10 billion chemical laboratories running experiments in molecular complexity across timescales measured in billions of years. Hold that number in your mind, because what follows depends on what you believe that number means. If the emergence of life is extraordinarily unlikely, requiring some fantastically rare coincidence of mineral catalysts, energy gradients, and molecular luck, then even 10 billion habitable worlds might produce only a handful of living planets. Perhaps life is a fluke, a 1 in a billion accident that happened to occur on Earth and almost nowhere else. Under this assumption, our galaxy might contain 10 or fewer biospheres, each one a lonely island of biology in an ocean of sterile rock and gas. But there are reasons to suspect life is not that rare. On Earth, life appeared remarkably quickly. The planet formed 4.5 billion years ago. The heaviest asteroid bombardment tapered off roughly 4 billion years ago, and the oldest confirmed chemical signatures of biological activity date to approximately 3.7 billion years ago. Life did not wait. It emerged almost as soon as conditions permitted, within a few 100 million years of the surface cooling enough for liquid water to persist. If life required an astronomically unlikely accident, you would expect it to take much longer to appear, perhaps billions of years of failed chemistry before the right combinations stumbled together. Instead, life showed up almost immediately, as though the chemistry of carbon and water leads to biology, with something approaching inevitability. This observation has led some astrobiologists to argue that life emerges readily wherever conditions allow. If that is true, the number of living worlds in our galaxy is not 10, it is billions. And if even a small fraction of those biospheres eventually produce intelligence, the Milky Way should contain numerous technological civilizations at any given moment. Define intelligence carefully here, because the word carries baggage. We are not talking about consciousness in the philosophical sense, or wisdom in the moral sense. We are talking about the capacity to manipulate the physical environment using tools and technology, the capacity to build radio transmitters, launch spacecraft, or otherwise make your presence detectable across interstellar distances. On Earth, this capacity emerged only once in 4.5 billion years of biological evolution, which suggests that while life may be common, technological intelligence may be considerably rarer. How much rarer is anyone's guess? The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicative civilizations in the galaxy by multiplying together a chain of probabilities. The rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, the fraction of living worlds that produce intelligence, the fraction of intelligent species that develop detectable technology, and the average lifespan of such civilizations. The equation is more useful as a framework for organizing ignorance than as a calculator of certainty. Most of its terms remain unknown, but even plugging in conservative values for each factor produces estimates ranging from a few to several thousand civilizations existing simultaneously in our galaxy. Let us adopt a deliberately moderate position. Assume that out of the billions of potentially habitable worlds in the Milky Way, life arises on roughly 1 in every million. That yields 10,000 living worlds. Assume that 1 in every 1,000 living worlds eventually produces a technological civilization. That gives us 10 civilizations active in the galaxy right now. 10 is a small number, vanishingly small compared to the 400 billion stars and the trillion planets. And yet 10 civilizations in a single galaxy would represent one of the most profound facts in the history of science. It would mean we are not alone. It would mean intelligence is a repeatable outcome of cosmic evolution. It would mean that somewhere, right now, another species is building instruments and asking the same questions we ask. But 10 civilizations also means something else, something less hopeful. It means those civilizations are extraordinarily far apart. The Milky Way is not a small place. It spans approximately 100,000 light-years from edge to edge. Its disk, where most stars and planets reside, measures roughly 2,000 light-years in thickness. Treating the galaxy as a flattened cylinder, its total volume encompasses something on the order of 15 trillion cubic light-years. That is the arena. 15 trillion cubic light-years of space, mostly vacuum, sprinkled with stars and planets separated by gaps measured in light-years. Now scatter 10 civilizations randomly across that volume. The mathematics of spatial distribution in 3 dimensions gives us the average nearest neighbor distance. For 10 points distributed uniformly through 15 trillion cubic light-years, the expected separation between closest neighbors works out to roughly 11,600 light-years. 11,600 light-years. Say it slowly and let the distance register. Light itself, moving at 300,000 kilometers per second, the absolute maximum speed permitted by the laws of physics, would need 11,600 years to cross that gap. A radio signal broadcast from one civilization would not reach its nearest neighbor until 116 centuries later. A reply would take equally long, producing a round-trip communication delay of more than 23,000 years. When the signal was sent, Earth's last ice age had not yet ended. By the time a reply returned, human civilization as we know it would be unrecognizable. Increase the number of civilizations and the distances shrink, but not as dramatically as intuition suggests. Volume scales with the cube of radius, so you need to multiply the number of civilizations by 8 to halve the nearest neighbor distance. 80 civilizations yield an average gap of roughly 5,800 light-years. 1,000 civilizations, an extremely optimistic figure, bring the average down to approximately 2,500 light-years. 2,500 light-years remains an almost incomprehensible distance. Even at velocities far beyond anything human technology has achieved, the journey times stretch across millennia and tens of millennia. At speeds that strain the limits of theoretical propulsion, the one-way trip to the nearest plausible neighbor still consumes thousands of years. When the ship departs, the Egyptian pyramids have not been built. By the time it arrives, every empire, every language, every cultural memory from the launch era has dissolved into archaeological dust. And that is the optimistic case. That is 1,000 civilizations, the most generous assumption, traveling at speeds whose energy costs border on the unimaginable. To ground these distances in something the human brain can attempt to process, consider an analogy. Shrink the entire Milky Way galaxy down to the size of the continental United States, roughly 3,000 miles from coast to coast. At this scale, our solar system becomes a speck smaller than a grain of pollen. The nearest star, Proxima Centauri, sits about 4 inches away. The 10 civilizations in our optimistic scenario are scattered across the country like 10 people randomly placed somewhere between New York and Los Angeles. The average distance between any two of those people is roughly 900 miles. No roads, no vehicles, no landmarks. Just open terrain stretching to the horizon in every direction. Each person knows the others exist somewhere out there, but cannot see them, cannot hear them, and has no way to reach them on foot within a human lifetime. Now restore the galaxy to its actual size. Replace miles with light years. Replace terrain with hard vacuum irradiated by cosmic rays and devoid of any resources, any fuel, any shelter. The distances between civilizations are not metaphors for loneliness. They are physical realities imposed by the geometry of a galaxy containing 400 billion stars spread across 100,000 light-years of space. Even when you assume intelligent life is common, the sheer volume of the Milky Way guarantees that each instance of intelligence sits in profound isolation. And our galaxy is just one among 2 trillion in the observable universe. Andromeda, the nearest major galaxy, lies 2.5 million light-years distant. The Virgo cluster sits 54 million light-years away. The observable universe stretches 93 billion light-years across. Civilizations arising in separate galaxies face distances so stupendously vast that the gaps within a single galaxy look almost cozy by comparison. Intergalactic contact does not merely require patience, it requires miracles that physics does not provide. The emptiness between stars deserves more attention than most discussions of interstellar travel grant it, because the void is not simply an absence, it is a presence. It is a physical environment with properties, hazards, and a character that makes it profoundly hostile to anything attempting to cross it. Interstellar space contains, on average, roughly 1 atom per cubic centimetre. For perspective, the air in the room where you are sitting contains approximately 25 billion molecules per cubic centimetre. Interstellar space is roughly 25 billion times emptier than your living room. If you could somehow remove all the air from a room and pump it down to the best vacuum achievable by the most advanced laboratory equipment on Earth, that vacuum would still contain roughly 10,000 molecules per cubic centimetre. Interstellar space is tens of thousands of times emptier than even that. It is a vacuum so thorough that individual atoms can travel for years without encountering another particle. But empty does not mean safe. The interstellar medium is also hostile. Cosmic rays, high-energy particles accelerated by ancient supernovae and other violent astrophysical processes, thread through interstellar space at all times. On Earth, our atmosphere and magnetic field absorb the most dangerous ones. A vessel in deep interstellar space has no such protection. Microscopic dust grains of silicate and carbon drift at vanishingly low densities, roughly 1 grain per 100,000 cubic meters, sparse beyond imagination but present across every light year of the journey. At low speeds, these hazards are manageable. At the velocities required for meaningful interstellar travel, they become something else entirely, a problem whose severity becomes apparent the moment we consider how fast a vessel must actually travel. And there is nothing else. No fuel depots, no rest stops, no raw materials that could be harvested to extend a journey or repair damage. No sources of energy beyond what the vessel carries or can capture from the faint glow of distant stars. The interstellar void is not merely empty. It is aggressively, hostilely, comprehensively devoid of anything useful to a traveller. A vessel that enters this void carries everything it will ever need for the entire duration of the journey, which may span millennia, or it does not survive. This is the arena. This is the playing field on which the drama of interstellar contact must unfold. Billions of potentially habitable worlds, strewn with absurd generosity across a galaxy 100,000 light-years wide, separated by chasms of vacuum so pure, so vast, and so hazardous that crossing even the shortest gap between neighbours demands capabilities that may exceed what physics allows. The numbers paint a picture that is simultaneously hopeful and devastating. Hopeful because the raw ingredients for life are everywhere. Rocky planets orbit in habitable zones around billions of stars. The chemistry of carbon and water operates identically in every corner of the galaxy. The processes of molecular evolution that produce life on Earth are not unique to Earth. They are consequences of universal physical laws applied to common cosmic materials. If life can arise here, it can arise anywhere the conditions match. And the conditions match in billions of locations. Devastating because those billions of locations are scattered across a volume so enormous that even the speed of light, the fastest thing permitted by the laws of nature, requires thousands of years to connect the nearest neighbours. The galaxy is not a neighbourhood. It is not a city. It is not even a continent. It is an ocean of emptiness, punctuated by rare, tiny, isolated islands of matter. And on some of those islands, chemistry has become biology, and biology has become intelligence, and intelligence has looked up at the stars and wondered whether anyone else is out there. The answer, almost certainly, is yes. The mathematics is too compelling, the opportunities too numerous, the chemistry too universal, for Earth to be the only world where molecules learn to think. But being out there and being reachable are two entirely different propositions. Existence does not guarantee contact. Abundance does not guarantee proximity. The universe creates life with breathtaking generosity, and then places each instance of life in a box of distance so large that escape seems almost inconceivable. Almost. Not certainly. Almost. And it is in that slender gap between almost and certainly that the next barriers reveal themselves. Because distance alone, however vast, is theoretically a problem of patience and engineering. Given enough time and enough energy, perhaps even 11,600 light-years could be crossed. The cosmos, however, does not grant unlimited time or unlimited energy. It imposes hard constraints on both, constraints woven into the deepest structure of physical law. The first of those constraints is a speed limit, not a speed suggestion, not a guideline, not a technological barrier that cleverer engineering might sidestep. A limit. Absolute, unyielding, confirmed by every experiment ever conducted in the history of physics. A wall built into the geometry of space-time itself. And behind that wall waits an energy abyss so deep that it swallows stars. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that quietly demolished any future hope of crossing the galaxy with ease. Albert Einstein was not trying to kill interstellar travel. He was trying to understand the relationship between space, time, and the speed of electromagnetic radiation. But the theory he produced, special relativity, revealed something so fundamental and so unyielding that more than a century of subsequent physics has only reinforced its authority. The speed of light is not merely a measurement, it is a structural property of space-time itself. It is the rate at which causality propagates through the universe, and nothing that carries mass, no ship, no probe, no passenger can ever reach it. The speed of light in vacuum measures approximately 299,792 kilometers per second. To give that number texture, a photon leaving the surface of the sun reaches Earth in roughly 8 minutes. That same photon could circle the entire planet 7.5 times in a single second. Light is so fast that for almost every purpose in daily human experience, it appears instantaneous. Flip a switch and the room illuminates. No perceptible delay, no waiting. The speed of light sits so far beyond human-scale motion that our ancestors can be forgiven for assuming it was infinite. It is not infinite, and the universe is built on scales that expose this finitude with ruthless clarity. Light requires 4 years and 3 months to reach the nearest star system, Alpha Centauri. It needs roughly 26,000 years to reach the center of our galaxy. It takes 100,000 years to cross the Milky Way from edge to edge. The most probable distance between neighboring civilizations measures somewhere between 2,500 and 11,600 light-years, depending on how many civilizations you assume exist. Even light, the fastest phenomenon permitted by the laws of physics, needs millennia to bridge these gaps. But the speed of light is more than just a cosmic speed limit. It is a wall with teeth. The closer any massive object approaches it, the more violently the universe pushes back. This is not a metaphor. It is a measurable, experimentally confirmed consequence of special relativity, and it manifests through three interlocking effects that together make relativistic travel an energy nightmare of almost incomprehensible proportions. The first effect is relativistic mass increase. As an object accelerates toward the speed of light, the energy required to accelerate it further does not grow linearly. It grows according to the Lorentz factor, a mathematical function that starts gently and then climbs toward infinity as velocity approaches c. At 50% of light speed, the Lorentz factor is approximately 1.15, meaning the effective resistance to further acceleration has increased by 15%. Manageable perhaps for a sufficiently advanced civilization. At 90% of light speed, the Lorentz factor reaches 2.29. The object now resists acceleration as though it had more than doubled its rest mass. At 99%, the factor climbs to 7.09. At 99.9%, it reaches 22.4, and it never stops climbing. The curve steepens without limit, approaching infinity as velocity approaches c. To actually reach the speed of light, you would need to supply infinite energy to any object with mass. Not a very large amount of energy, not an astronomically large amount, infinite. This is not an engineering limitation awaiting a clever workaround. It is a mathematical boundary as firm as the statement that you cannot divide by zero. The second effect is time dilation. A clock aboard a vessel moving at a significant fraction of light speed ticks more slowly than a clock at rest. At 50% of c, time aboard the ship passes at roughly 87% the rate of stationary time. At 90%, the ratio drops to about 44%. At 99%, time aboard the vessel crawls at barely 14% of the external rate. For the travellers, the journey feels shorter. But for everyone else, for the civilization that launched them, for the civilization they are travelling toward, the full, uncompressed duration passes. A crew experiencing 20 years of shipboard time at 90% of c would return to find that 46 years had elapsed at home. At 99%, the same 20 subjective years would correspond to 143 years in the external universe. Time dilation is sometimes presented as a loophole, a way to cheat the distance problem by compressing the subjective journey. And for the travellers, it does compress the experience. But it does nothing to compress the external duration. The sending civilization must wait the full travel time. The receiving civilization must still exist when the vessel arrives. The universe does not grant discounts on elapsed time merely because the passengers experience less of it. Time dilation is a perceptual shift, not a shortcut. It changes who suffers the wait. It does not reduce the wait itself. The third effect is length contraction. From the perspective of a vessel moving at relativistic speeds, distances in the direction of travel appear compressed. At 90% of c, the distance to a star 10 light-years away appears to shrink to roughly 4.4 light-years from the ship's frame of reference. Again, this sounds advantageous. But the contraction is frame-dependent. Observers at the origin and destination measure the full uncontracted distance. The energy required to make the trip corresponds to the full distance as measured in the rest frame, not the compressed distance perceived aboard the ship. Length contraction changes what the travellers see. It does not change what the journey costs. These three effects are not theoretical speculations. They are among the most thoroughly verified predictions in all of physics. Every particle accelerator on Earth confirms relativistic mass increase every time it operates. The Large Hadron Collider at CERN accelerates protons to 99.99991% of light speed, and the energy required to push those protons through that final infinitesimal fraction matches Einstein's equations to extraordinary precision. Time dilation has been confirmed using synchronized atomic clocks flown on aircraft and satellites. The global positioning system would drift by roughly 10 kilometers per day if its software did not correct for relativistic time differences between orbiting satellites and ground-based receivers. Special relativity is not a hypothesis. It is operational technology. Now, apply these principles to the problem of interstellar travel and observe what happens to the energy budget. Consider a spacecraft with a payload mass of 1,000 metric tons. This is roughly the mass of a large naval destroyer, a vessel capable of carrying several hundred crew members along with life support systems, provisions, and scientific equipment. It is a modest payload by the standards of a civilization attempting to cross interstellar distances, barely sufficient for a skeleton crew on a one-way journey. A more realistic crewed vessel might mass 10 or 100 times more, but start with 1,000 tons to give the physics every possible advantage. The energy costs of accelerating this vessel reveal a staircase of escalating impossibility that deserves a slow, methodical climb. Each step upward in velocity does not simply add difficulty. It multiplies difficulty, compounding on the step before it in a progression that rapidly overwhelms any conceivable energy source. At 1% of the speed of light, roughly 3,000 kilometers per second, the vessel moves faster than any macroscopic object humans have ever propelled. The New Horizons probe, the fastest spacecraft humanity has launched, reached approximately 16 kilometers per second. 1% of c is nearly 200 times faster. The kinetic energy required is approximately 4.5 times 10 to the 18th joules. This is roughly equivalent to the energy released by the largest thermonuclear weapon ever detonated, the Soviet Tsar bomber, multiplied by 20. It approaches 1% of humanity's total annual energy consumption, directed into a single object. It is a staggering amount of energy directed at a single object, but it falls within the theoretical reach of a civilization that has mastered nuclear fusion and can direct its output efficiently. The problem is that 1% of c is uselessly slow for the distances involved. At this velocity, the journey to a neighbour 2,500 light-years away takes 250,000 years. That is longer than the entire existence of anatomically modern humans. The vessel would arrive at its destination long after the species that built it had either gone extinct or evolved beyond recognition. At 10% of the speed of light, the journey compresses to 25,000 years. Still enormous, but conceivably within the lifespan of a civilization that endures for 1,000,000 years. The kinetic energy, however, has not merely increased tenfold, it has increased roughly 100-fold, to approximately 4.5 times 10 to the 20th joules. This is roughly equivalent to the total energy consumption of human civilization over an entire year. Every power plant, every reactor, every engine on Earth running for 12 months, poured into a single spacecraft. That is the energy budget for acceleration alone. Deceleration upon arrival doubles it. The round trip, if one is contemplated, quadruples it. A civilization that can marshal an entire year of global energy output into a single propulsion event is operating at a level of engineering so far beyond current human capability that it qualifies as science fiction. And this is merely the kinetic energy of the payload. The rocket equation demands that the total mission energy, including fuel, be vastly larger still, and yet 10% of c barely dents the distance problem. At 30% of the speed of light, the journey to a neighbour 2,500 light-years away takes roughly 8,300 years. Relativistic effects are beginning to bite, adding roughly 5% to the effective mass. The kinetic energy climbs to approximately 4.3 times 10 to the 21st joules. This exceeds the total energy consumption of human civilization over 7 consecutive years. Every power plant, every reactor, every solar panel, every combustion engine on Earth, running continuously for 7 years, produces roughly the energy needed to accelerate one modest spacecraft to 30% of the speed of light. And once again, this accounts only for acceleration. Including deceleration for a controlled arrival, doubles the requirement to 14 years of total global energy output. This is only the payload kinetic energy. When the rocket equation compounds the fuel mass needed to deliver this velocity, the total mission energy climbs by additional orders of magnitude, approaching and eventually exceeding stellar output. At 50% of the speed of light, the journey takes 5,000 years. Relativistic mass increase has added roughly 15% to the effective payload. The kinetic energy reaches approximately 1.4 times 10 to the 22nd joules. This exceeds the total energy consumption of human civilization over 24 consecutive years. Nearly a quarter century of every joule produced on Earth, directed at a single vessel, and this is merely the kinetic energy of the payload alone, ignoring the fuel. When the rocket equation is applied, a fusion-powered vessel carrying enough fuel to reach 50% of C and then decelerate upon arrival requires a fuel-to-payload ratio exceeding 200 million to 1. The total mass of fuel exceeds that of a large asteroid. The total energy budget for the complete mission, including fuel production and expenditure, climbs into the range of minutes of total solar output. We have left the realm of planetary engineering and entered the realm of stellar engineering. And this is for one ship carrying 1,000 tons on one journey in one direction. At 90% of the speed of light, the Lorentz factor has more than doubled the effective mass of the vessel. The kinetic energy climbs to approximately 1.6 times 10 to the 20th joules. This is roughly 200 years of total human energy consumption packed into the kinetic energy of a single vessel. But the kinetic energy is only the beginning. The rocket equation at 90% of C with fusion propulsion demands a fuel-to-payload ratio so extreme that the total fuel mass exceeds the mass of a small planet. The total mission energy for a one-way trip with deceleration climbs to the equivalent of more than a century of total solar output, not seconds, not minutes. More than 100 years of every joule the sun produces, funneled into the acceleration and deceleration of a single vessel carrying a payload roughly the weight of a naval destroyer. A Kardashev Type II civilization, one that captures the entire energy output of its host star, would need to save that energy for over a century before it could afford a single round trip at 90% of light speed. And the sun is a modest star. Civilizations orbiting dimmer red dwarfs would face energy deficits even more severe. This escalation is not incidental. It is the defining feature of relativistic physics applied to propulsion. The energy does not scale linearly with velocity. It does not even scale quadratically, as it would under classical Newtonian mechanics. It follows a curve that steepens relentlessly as velocity increases, punishing every additional kilometer per second with disproportionately greater energy demands. The universe has structured its physics to make slow travel cheap and fast travel ruinously expensive, with the cost rising toward infinity as the speed of light is approached. The rocket equation makes these figures even worse. Any vessel that carries its own fuel must account for the mass of that fuel, which itself must be accelerated along with the payload. This creates a compounding problem. To carry enough fuel to reach high velocity, you need more fuel to carry the fuel, which requires more fuel to carry that fuel, and so on. The equation spirals exponentially. For a chemical rocket, reaching even 1% of light speed requires a fuel-to-payload ratio so extreme that the fuel mass exceeds the mass of the observable universe. Chemical rockets are obviously inadequate for interstellar travel at any speed relevant to crossing the distances separating civilizations in our galaxy. They are ruled out not by insufficient cleverness but by the energy density of chemical bonds, which falls short of the requirement by many orders of magnitude. Nuclear fusion improves the picture considerably. Fusion of deuterium and helium-3 converts approximately 0.4% of the fuel mass into energy, a dramatic improvement over chemical combustion. A fusion-powered spacecraft could theoretically achieve velocities of several percent of light speed with fuel-to-payload ratios in the range of 10s to 1. This is the basis for many serious interstellar mission concepts, including Project Daedalus, A study conducted by the British Interplanetary Society in the 1970s, which proposed a fusion-powered probe capable of reaching Barnard's star at roughly 12% of light speed. But Project Daedalus was an uncrewed flyby mission with a payload of roughly 450 metric tons. The vessel itself, fully fueled, massed approximately 54,000 metric tons. The fuel-to-payload ratio exceeded 100 to 1, and the mission reached only 12% of C, a speed at which the journey to a neighbour 2,500 light-years away would still consume more than 20,000 years. To significantly increase the velocity, the fuel ratio climbs exponentially. At 30% of C, the ratio reaches thousands to 1. At 50%, it enters a regime where the required fuel mass exceeds the mass of large asteroids. The exponential scaling of the rocket equation is not a technical problem. It is a mathematical structure inherent to any propulsion system that carries its own reaction mass. Every kilogram of fuel you add requires additional fuel to accelerate that kilogram, which requires additional fuel to accelerate the additional fuel. The compounding is relentless. At relativistic velocities, it becomes a cage from which no chemical, nuclear, or fusion propulsion system can escape without fuel masses that exceed the mass of planets. Matter-antimatter annihilation offers the ultimate theoretical energy density. When a particle of matter meets its antiparticle, both are converted entirely into energy according to Einstein's E equals mach squared. This represents 100% mass-to-energy conversion, roughly 250 times more efficient than the best fusion reactions. A matter-antimatter drive could theoretically achieve velocities approaching the speed of light with fuel-to-payload ratios in the single digits. The problem is that antimatter does not exist naturally in usable quantities anywhere in the known universe. Every antiproton used in physics research is manufactured in particle accelerators, one atom at a time, at staggering energy cost. The total antimatter produced by every accelerator on Earth since the technology was invented amounts to roughly 20 nanograms. Producing 1 gram of antimatter at current accelerator efficiencies would require energy inputs so vast they rival the annual electrical output of entire nations. Producing the kilotons of antimatter needed for an interstellar voyage would require energy inputs exceeding the total output of the Sun over extended periods. This creates a paradox that illustrates the depth of the energy barrier. The most efficient, conceivable fuel requires more energy to manufacture than the fuel itself will provide. You must spend stellar-scale energy to produce the antimatter, then burn the antimatter to propel a vessel that could not carry enough fuel to reach relativistic speeds without the antimatter. The efficiency advantage is real in principle but inaccessible in practice. The universe allows matter-antimatter annihilation. It just makes the antimatter nearly impossible to acquire. Some propulsion concepts attempt to sidestep the rocket equation entirely by not carrying fuel. Solar sails and laser-driven light sails use external energy sources, typically powerful laser arrays, to accelerate a spacecraft by radiation pressure. The Breakthrough Starshot initiative proposes exactly this approach. An array of ground-based lasers focusing a combined beam of 100 gigawatts onto a gram-scale probe equipped with a reflective sail a few meters wide. The probe would accelerate to roughly 20% of C within minutes, reaching the Alpha Centauri system in approximately 20 years. This is an elegant concept for robotic exploration of nearby stars, but it does not solve the problem of physical contact between civilizations. A gram-scale probe cannot carry passengers. It cannot carry life support systems. It cannot decelerate upon arrival because no laser array exists at the destination to slow it down. It screams through the target system at 60,000 kilometers per second, collecting data during a flyby that lasts hours at most. For sending information about a nearby star, laser-propelled probes are promising. For establishing physical meetings between civilizations thousands of light-years apart, they are irrelevant. Scaling the laser sail concept to larger payloads introduces its own catastrophic problems. Radiation pressure scales linearly with sail area, but the mass of the payload scales with volume. Increasing the payload from 1 gram to 1,000 metric tons, the minimum mass for a crewed vessel, requires increasing the laser power by a factor of 1 billion. A 100 gigawatt laser array is an extraordinary engineering challenge. A 100 exawatt laser array is a concept so far beyond current capability that it borders on the meaningless. The energy required to power such an array during the acceleration phase would exceed the total energy output of every power plant on Earth combined, sustained for the duration of the burn. Theoretical concepts like the Alcubierre warp drive propose even more radical approaches, bending space-time itself to create a bubble of flat space that moves faster than light relative to the external universe. The mathematics of general relativity technically permit such solutions, but they require exotic matter with negative energy density, a substance that has never been observed in nature and may not be physically possible. Even if exotic matter could be produced, calculations suggest the energy required to sustain a warp bubble capable of carrying a spacecraft would be equivalent to the total mass energy of a planet, or in some formulations, an entire star converted completely into exotic matter. These speculative propulsion concepts deserve mention precisely because they illustrate the scale of the barrier. When the most optimistic theoretical physics requires converting Jupiter into exotic matter to move a single vessel faster than light, the universe is telling you something about the difficulty of the problem. These are not solutions waiting to be unlocked by better engineering. They are mathematical curiosities that highlight how severely physics constrains relativistic and superluminal travel. Strip away the speculation, and you are left with a hard physical reality. The speed of light cannot be reached by any object with mass. Approaching it demands energy that scales exponentially with velocity, and the propulsion systems that might deliver meaningful fractions of c require either fuel masses exceeding planets or energy inputs exceeding stars. This is not a single barrier, it is two barriers compounding each other. The speed limit and the energy scaling are independent constraints arising from the same underlying physics. The speed limit alone would make interstellar travel slow. The energy scaling alone would make it expensive. Together, they create a trap. You cannot go fast enough to cross the distances in reasonable time, and you cannot afford the energy to go fast enough to try. Consider what this means in practice. A technological species arises on a habitable world orbiting a star in the Milky Way. It develops physics, discovers relativity, maps the sky, and identifies a candidate signal or observation suggesting another civilization exists 2,500 light-years away. It decides to make contact, not by radio, which would require 5,000 years for a round trip, but physically. It wants to send a vessel. At 1% of light speed, achievable perhaps with advanced fusion propulsion and a fuel-to-payload ratio in the hundreds, the journey takes 250,000 years. The entire recorded history of human civilization fits into the last 2% of that duration. No known institution, no biological species in an unchanged form, has persisted for such a span. At 10% of light speed, requiring fuel masses rivaling small moons, the trip takes 25,000 years. Shorter, but still longer than any civilization in the human record has endured without radical transformation. At 50% of light speed, the journey compresses to 5,000 years. But the energy required to accelerate a crewed vessel to half the speed of light, accounting for the fuel demanded by the rocket equation and deceleration upon arrival, approaches the total energy output of a star over several minutes. The civilization must harness and direct stellar-scale energy toward a single purpose, sustained long enough to complete the acceleration burn, without any guarantee that the destination civilization still exists. At 90% of light speed, barely achievable even in principle due to the Lorentz factor's steep climb, the trip takes approximately 2,700 years. The total mission energy, including the fuel mass demanded by the rocket equation, approaches the total output of a star sustained over decades to centuries, depending on the propulsion system assumed. Time dilation compresses the subjective journey to roughly 1,200 years for the crew, but the external universe still ages 27 centuries. The civilization that launched the vessel must maintain its identity and purpose across that entire span, or the mission becomes an archaeological curiosity dispatched by a society that no longer exists. None of these scenarios account for the challenges of surviving the journey itself. Interstellar space is threaded with cosmic radiation, high-energy protons and heavier nuclei accelerated to relativistic speeds by supernova remnants and other astrophysical engines. At rest, this radiation is manageable with sufficient shielding, but a vessel moving at a significant fraction of c encounters these particles at vastly amplified energies due to relativistic effects. A proton striking a ship's hull at 50% of c carries enough energy to damage molecular bonds and ionize atoms along its path. Individually, these impacts are microscopic. Collectively, over decades and centuries of exposure, the cumulative radiation dose from trillions of such impacts becomes lethal to biological tissue and degrading to electronic systems. At 90% of c, every stray hydrogen atom in the interstellar medium becomes a source of intense ionizing radiation, and the cumulative bombardment across years of travel would degrade hull materials, destroy unshielded electronics, and deliver lethal radiation doses to any biological crew. Shielding against this bombardment adds mass, which increases the fuel requirement, which compounds the energy problem. Dust grains, rare but present in interstellar space, become devastating at relativistic velocities. A grain of dust massing 1 milligram, striking a vessel at 50% of the speed of light, releases energy roughly equivalent to 3 metric tons of high explosive. A single invisible speck of interstellar dust hits with the force of a large conventional bomb. At 90% of c, the same grain delivers energy exceeding 25 metric tons of TNT, comparable to the largest conventional explosives ever detonated, and that is a single milligram of dust. A grain of sand, massing perhaps 50 milligrams, would strike with the force of over a kiloton of explosive. Navigating through even the sparse medium of interstellar space at these speeds demands either extraordinary shielding, extraordinary luck, or some method of detecting and deflecting particles at ranges allowing reaction time measured in fractions of a second. The cumulative weight of these constraints bears repeating because the implications are so severe. The speed of light is a hard ceiling. Energy requirements scale exponentially as you approach it. Fuel logistics compound the energy problem through the rocket equation. The interstellar medium becomes increasingly lethal at higher velocities. And even if all these challenges are overcome, the journey still requires centuries or millennia, during which both the sending and receiving civilizations must persist. It is tempting to imagine that a civilization millions of years more advanced than humanity might find solutions invisible to our current understanding. And this is true in the sense that we cannot predict what future science will discover. But special relativity is not a provisional theory awaiting replacement. It is a framework so deeply embedded in the structure of physics that overturning it would require dismantling electromagnetism, particle physics, and cosmology simultaneously. No serious physicist expects this to happen. The speed of light is as permanent a feature of reality as the existence of matter itself. The universe permits interstellar travel in principle. It does not forbid a vessel from crawling across the void at 1% of light speed over hundreds of thousands of years. What it forbids is doing so quickly, efficiently, or within the lifespan of any known type of civilization. The speed limit and the energy abyss together transform interstellar distances from a challenge of engineering into a constraint of physics, and physics does not negotiate. But even this devastating combination of barriers does not tell the full story. Speed and energy address the question of whether a vessel can cross the gap. They do not address the question of whether anyone will be waiting on the other side when it arrives. The universe imposes yet another constraint, one that operates not in space or energy but in time. And time, it turns out, may be the cruelest barrier of all. There is a thought experiment that strips away every comfortable assumption about interstellar contact. Imagine you live in a vast apartment building with 10,000 units spread across 500 floors. You know other tenants exist because you can hear muffled sounds through the walls. But there is a catch. Each tenant occupies their apartment for only 15 minutes out of every year. They arrive at random times, stay briefly, and leave. You have no schedule, no directory, no way to predict when anyone else will be home. Your 15 minutes might fall at 3 in the morning on a Tuesday in March. Your nearest neighbour's 15 minutes might land on a Saturday afternoon in October. You could live in that building for decades and never overlap with another living soul. Not because the building is empty, not because the tenants do not exist, but because the windows of occupancy are so brief and so randomly distributed that simultaneous presence becomes an event of extraordinary rarity. This is the temporal predicament of civilizations in the Milky Way. The galaxy is not merely vast in space, it is vast in time. And the fraction of that time during which any given civilization exists and possesses the technology to attempt interstellar travel is so vanishingly small that the odds of two civilizations sharing the same temporal window, while also sharing a crossable spatial gap, approach the negligible. Start with the age of the galaxy itself. The Milky Way began assembling roughly 13 billion years ago, within the first billion years following the Big Bang. The earliest stars formed from primordial hydrogen and helium, burning fast and dying violently in supernovae that seeded the interstellar medium with heavier elements. Carbon, oxygen, silicon, iron, the building blocks of rocky planets and organic chemistry, all were forged in the cores and explosions of those first stellar generations. By roughly 10 billion years ago, the galaxy's chemical enrichment had reached levels sufficient for the formation of terrestrial worlds with the molecular complexity necessary for biology. Earth formed 4.5 billion years ago from the debris of earlier stellar generations. Life appeared within the first billion years of the planet's existence. Multicellular organisms took another 2.5 billion years to emerge. Complex animals appeared roughly 540 million years ago. Mammals arose 200 million years ago. The genus Homo appeared roughly 2.5 million years ago. Anatomically modern humans have existed for approximately 300,000 years. And technological civilization, defined as the capacity to build machines, transmit electromagnetic signals, or otherwise make our presence detectable across interstellar distances, has existed for approximately 2 centuries. 2 centuries out of 13 billion years. If you compress the entire history of the Milky Way into a single calendar year, with the galaxy forming at midnight on January 1st, human technological civilization would occupy the final 5/10,000ths of a second before midnight on December 31st. Not the final second, not the final millisecond. A fraction of a millisecond, so small that it rounds to 0 on any scale the human mind can intuitively grasp. This brevity is not necessarily unique to humanity. It may reflect a general truth about the nature of technological civilizations. Consider the forces that constrain how long any civilization might persist in a state capable of interstellar travel. Natural catastrophes operate on timescales that intersect uncomfortably with civilizational lifespans. Asteroid impacts capable of triggering mass extinctions occur roughly once every 100 million years. The Chicxulub impactor that ended the age of dinosaurs 66 million years ago struck with the energy of billions of nuclear weapons, igniting global firestorms and plunging Earth into years of impact winter. Events of that magnitude reset the biological clock, erasing hundreds of millions of years of evolutionary progress in a geological instant. A civilization that has not yet developed the technology to deflect such an object, or one that has but fails to detect the threat in time, ceases to exist. Supernovae within a few dozen light years, close enough to irradiate a planet's surface and destroy its ozone layer, occur at intervals estimated in the hundreds of millions of years. Gamma-ray bursts, the most energetic explosions in the universe, could sterilize a planet's biosphere from thousands of light years away. Though their frequency and directionality make precise risk estimates difficult, none of these events are frequent on human timescales, but on galactic timescales, they are routine. A civilization that persists for 10 million years is virtually guaranteed to face at least one existential natural threat, Self-inflicted risks may be even more pressing. Industrial civilizations alter their environments at rates that can outpace adaptive responses. Climate destabilization, resource depletion, ecosystem collapse, nuclear arsenals, engineered pathogens, and the unpredictable consequences of artificial intelligence all represent threats that operate on timescales of centuries, not millions of years. If any of these pressures commonly leads to civilizational collapse before interstellar capability is achieved, the average lifespan of a technological civilization could be far shorter than the optimistic estimates many analyses assume. Even without catastrophe, civilizations might not remain interested in physical exploration indefinitely. A species that develops sufficiently advanced computation might retreat into virtual environments, effectively abandoning the physical universe in favor of simulated realities consuming far less energy. A civilization that masters genetic engineering might transform itself into forms unrecognizable as technological agents, becoming something closer to a distributed biological network than a tool-using species. These possibilities are speculative, but they highlight an important asymmetry. There are many ways for a civilization to stop attempting interstellar travel, and very few reasons to sustain that attempt across geological timescales. For the purposes of this analysis, grant the most generous assumption plausible. Assume that a typical technological civilization persists for 1 million years. This is more than 5,000 times longer than humanity has possessed any form of technology, and roughly 3 times longer than the entire existence of the genus Homo. 1 million years represents extraordinary persistence, a civilization that survives every natural disaster, solves every self-inflicted crisis, and maintains interest in physical outreach across time spans that would see continents drift measurably across a planet's surface. Even with this generous assumption, the mathematics of temporal overlap are devastating. The galaxy has existed for roughly 13 billion years. A civilization lasting 1 million years occupies approximately 1/13,000th of that total span. Stated differently, if you selected a random moment from galactic history, the probability that it falls within any particular civilization's window of existence is roughly 0.008%. The window is open for an instant and then it closes, permanently, as the civilization either perishes, transforms, or withdraws. Now consider 2 civilizations arising independently at random times during the galaxy's history. The probability that their million-year windows overlap at all depends on a simple geometric calculation. 2 intervals of length 1 million years, placed randomly on a timeline of 13 billion years, have an overlap probability of approximately 1 in 6,500, meaning if you repeated the experiment 6,500 times, you would expect the 2 windows to overlap only once. For overlap to enable physical contact, the civilizations must not only coexist in time, but must also be close enough in space for a journey to be completed within the remaining overlap window. Recall the geometry. 10 civilizations spread across the Milky Way, places the nearest neighbours roughly 11,600 light-years apart. Even at 10% of the speed of light, which requires energy rivaling a civilization's entire annual output, the journey between nearest neighbours takes 116,000 years. This exceeds the assumed civilizational lifespan of 1 million years by more than a tenth. The journey consumes over 10% of the civilization's entire technological existence. For the journey to succeed, several conditions must be met simultaneously. The sending civilization must detect the receiving civilization, which requires that both are active and producing detectable signatures at the same time. The sending civilization must develop and launch an interstellar vessel, a process that could itself require centuries or millennia of technological development. The vessel must survive the journey, which at 10% of C means enduring 116,000 years of exposure to cosmic radiation, interstellar dust impacts, mechanical degradation, and the accumulated failures of systems never designed to operate on such timescales. And the receiving civilization must still exist when the vessel arrives. It must not have destroyed itself, evolved beyond recognition, abandoned its planet, or simply ceased producing the signals that attracted the sender's attention in the first place. Each of these conditions carries its own probability of failure. Stack them together, and the compound probability of a successful physical meeting drops precipitously with each additional requirement. But the temporal problem extends beyond civilizational lifespans. The stars themselves impose deadlines that no civilization can negotiate. Stars are not permanent. They are engines that burn through finite fuel supplies at rates determined by their mass. The relationship between a star's mass and its lifespan is not linear. It is steeply inverse. Double the mass, and the star does not burn twice as fast. It burns roughly 8 to 10 times faster, because higher mass means higher core temperatures, which accelerate nuclear fusion at rates that far outpace the extra fuel supply. This means the galaxy's stellar population offers radically different habitable windows depending on which star a civilization happens to orbit. The Sun, a G-type main-sequence star with a mass of roughly 1 solar mass, has a total hydrogen-burning lifespan of approximately 10 billion years. It is currently 4.5 billion years into that lifespan, leaving roughly 5.5 billion years before it exhausts its core hydrogen, expands into a red giant, and eventually sheds its outer layers to become a white dwarf. Long before that final stage, the Sun's increasing luminosity will render Earth uninhabitable. Within roughly 1 billion years, solar output will have increased enough to trigger a runaway greenhouse effect, boiling away Earth's oceans and sterilizing the surface. The habitable window for our planet is not 5 billion years. It is closer to 1 billion, perhaps 1.5 billion at most. Consider an F-type star, roughly 1.3 times the mass of the Sun. These stars burn hotter and bluer, pouring out more energy per second. Their total main sequence lifespan drops to approximately 4 to 5 billion years. The habitable zone around such a star shifts outward more quickly as the star brightens, leaving planets less time to develop complex ecosystems. If intelligence requires the roughly 4 billion years of prior biological evolution that it took on Earth, F-type stars are marginal hosts. Their habitable windows close before the biological clock finishes ticking. Move up to A-type stars, at roughly twice the solar mass, and the picture becomes hopeless for biology as we understand it. These stars exhaust their hydrogen in under 2 billion years. Their habitable zones shift so rapidly that stable planetary climates may never form. Whatever worlds orbit these stars face conditions that change faster than evolution can adapt. A-type stars are brilliant, numerous, and biologically irrelevant. They burn too fast for life to get a foothold. At the other extreme, red dwarfs of spectral type M constitute roughly 70% of all stars in the galaxy. A red dwarf of 0.1 solar masses burns so frugally that its lifespan stretches to roughly 10 trillion years, nearly 1,000 times the current age of the universe. On paper, this seems ideal. A planet orbiting a red dwarf has an almost unlimited window for life to emerge and develop. But red dwarfs present severe and possibly disqualifying obstacles. Their habitable zones lie so close to the star that planets become tidally locked, permanently showing one face to their sun. The illuminated hemisphere bakes under perpetual daylight while the dark hemisphere freezes in permanent night. Whether a stable, life-supporting climate can develop under such conditions remains an open and vigorously debated question. Red dwarfs also produce frequent and violent flares, sudden eruptions of radiation that can exceed the star's normal luminosity by factors of hundreds or thousands for minutes to hours. A planet orbiting within the habitable zone of an active red dwarf endures periodic radiation storms that can strip its atmosphere in geological instants. A planet that loses its atmosphere loses its water. A planet without liquid water loses its chance at life as we understand it. K-type stars, sometimes called orange dwarfs, occupy an intriguing middle ground. With masses between roughly 0.6 and 0.9 solar masses, they burn steadily for 15 to 30 billion years, more than enough time for intelligence to evolve. They are less prone to violent flaring than red dwarfs. Their habitable zones sit at distances where tidal locking is less certain. Some astrobiologists consider K-type stars the most promising hosts for long-lived biospheres, offering the stability of a red dwarf without the hazards. But K-type stars are less numerous than red dwarfs, and their habitable windows, while long, still begin and end at specific times in galactic history, depending on when each star formed. This diversity of stellar lifespans creates a patchwork of habitable windows scattered across the galaxy in both space and time. Some star systems reached habitable conditions 8 or 9 billion years ago and have already passed through their window. Whatever civilizations arose around those stars lived and died before our sun even ignited. Their worlds may still orbit, but as barren husks long since sterilized by their aging stars, others became habitable more recently, within the last few billion years, and remain within their window. Still others, particularly around younger stars or in regions of the galaxy where metallicity is still increasing through ongoing stellar nucleosynthesis, have not yet reached conditions suitable for complex life and will not do so for billions of years to come. This temporal patchwork means that two civilizations need not only exist simultaneously, but must also arise around stars whose habitable windows overlap. A civilization that emerged 7 billion years ago around a star that has since left the main sequence cannot be visited today. Its star may be a white dwarf, its planets either consumed during the red giant phase or stripped to barren cores orbiting a stellar remnant. A civilization that will not emerge for another 3 billion years around a young star currently in its early main sequence phase cannot be visited either. It does not yet exist. The travelers would arrive to find a world still billions of years from producing intelligent life. And here lies a particularly cruel dimension of temporal isolation that deserves explicit attention. Imagine a civilization that detects a promising signal from a star system 4,000 light-years away. They invest centuries of effort into building an interstellar vessel. They launch it at 5% of the speed of light, the maximum their energy budget allows. The journey takes 80,000 years. During those 80,000 years, the crew, whether biological beings in suspended animation or digital minds running in slow cycles, crosses a void of unimaginable emptiness. They endure cosmic ray bombardment, micrometeorite erosion, the slow degradation of systems pushed far beyond their designed operational lifetimes. And they arrive. They reach the star system that broadcast the signal. They enter orbit around the planet that showed spectral signatures of an oxygen-rich atmosphere and artificial electromagnetic emissions. What they find is silence. The planet's atmosphere has changed. The oxygen signature is gone, replaced by carbon dioxide and methane. The surface, viewed from orbit, shows no artificial structures, no city lights on the night side, no electromagnetic transmissions of any kind. The oceans are still there, but they have turned a deep reddish brown, choked with anaerobic microorganisms that have reclaimed a world left empty. The civilization that sent the signal is gone. Perhaps it destroyed itself. Perhaps it evolved into something unrecognizable. Perhaps a natural catastrophe, a supervolcanic event, an asteroid impact, a nearby stellar flare, wiped the slate clean 50,000 years before the vessel arrived. The travellers crossed 80,000 years of void to find a graveyard, not the bones of individual beings, which would have long since decomposed, but the graveyard of an entire species, detectable only as a subtle chemical disequilibrium in a planet's atmosphere slowly returning to abiotic baseline. Or consider an even more haunting variant. The travellers arrive and find the planet thriving, covered in life, oceans blue and continents green. But the life is not intelligent. It is complex, multicellular, even diverse, but it has not yet produced minds capable of recognizing visitors. The civilization the travellers sought existed 85,000 years ago. It lasted 300,000 years, produced art and science and radio signals and dreams of the stars. And then it ended. The biology of its homeworld continued without it, filling the ecological niches the departed civilization left behind. The planet is alive. The civilization is extinct. The travelers have arrived 60,000 years too late to meet anyone, but early enough to see the world their hoped-for hosts once inhabited, now populated by creatures that will never know what walked there before them. These scenarios are not dramatic embellishments, they are straightforward consequences of the mathematics. When journey times are measured in tens of thousands of years and civilizational lifespans are measured in hundreds of thousands to millions of years, the probability of arriving during the narrow window of a destination civilization's technological existence is small, and the probability that you will know in advance whether that window is still open is essentially zero. The signal you detected left the source thousands of years ago. By the time you receive it, the source civilization has aged by exactly the light travel time of the signal. A signal received from 4,000 light years away tells you about conditions 4,000 years ago. The civilization could have vanished 3,900 years ago, and you would not know for another century. The window of mutual reachability between two civilizations is therefore not determined by the galaxy's age or even by the civilization's lifespans alone. It is determined by the intersection of three independent time constraints: the habitable window of the first star, the habitable window of the second star, and the technological lifespan of each civilization within those windows. All three must overlap simultaneously, and the overlap must be long enough for a journey between them to be completed. Calculate this intersection for realistic parameters. Take two sun-like stars whose habitable windows span 6 billion years each, beginning at random times within the galaxy's history. The probability that their habitable windows overlap is significant, roughly 40 to 50%, because the windows are long relative to galactic time. But within those overlapping habitable windows, each civilization occupies only 1 million years. The probability that both civilizations exist simultaneously within the shared habitable window drops to roughly 1 in 3,000. And within that slim overlap, the civilizations must also be close enough for travel to be completed within the remaining window, which depends on the velocity achievable and the distance involved. For a separation of 5,000 light-years and a travel speed of 10% of c, the one-way journey time is 50,000 years. This means the overlap window must be at least 50,000 years long for the vessel to arrive while the destination civilization still exists. But a million-year window contains only 20 non-overlapping 50,000-year segments. If two civilizations each occupy a random million-year interval within a shared 6 billion-year habitable window, the probability that their intervals overlap by at least 50,000 years is roughly 1 in 3,200. And this assumes perfect knowledge of the destination's existence and location, instantaneous launch capability, and a travel speed that requires planet-scale energy expenditure. Stars also move. The Milky Way is not a static grid of fixed stellar positions. It is a rotating disk in which stars orbit the galactic center, at varying speeds depending on their distance from the core. The Sun orbits at roughly 220 kilometers per second, completing one full revolution every 230 million years. Over 50,000 years of travel time, the destination star moves approximately 37 light-years due to its own orbital motion. 37 light-years. The target drifts farther than the distance to some of our nearest stellar neighbours during a single journey time. Over 500,000 years, the displacement grows to nearly 370 light-years. Over 5 million years, 3,700 light-years, the destination does not merely drift, it relocates to an entirely different region of the galaxy. A vessel launched toward a star's current position arrives to find empty space, unless its trajectory accounts for the target's orbital motion across the entire journey duration. At these timescales, the trajectories become fiendishly complex. Stars do not move in simple circles. They oscillate vertically through the galactic disk, bobbing above and below the midplane in cycles lasting roughly 60 to 70 million years. They experience gravitational perturbations from spiral arms, which rotate at a different angular velocity than the stars themselves, creating density waves that tug on stellar orbits as they pass through. Encounters with giant molecular clouds, regions of dense gas weighing millions of solar masses, deflect stellar paths unpredictably. The cumulative effect of these perturbations means that predicting a star's precise position 50,000 years into the future requires knowledge of the galactic gravitational field to a degree of accuracy that may exceed the calming capabilities of any conceivable observational program. Over longer timescales, the prediction problem becomes essentially chaotic. The destination is not a fixed point on a map. It is a moving target following a path that grows increasingly uncertain with every additional century of projection. Now compound every barrier discussed so far. The galaxy contains perhaps 10 to 1,000 civilizations at any given moment, separated by thousands to tens of thousands of light years. Crossing those distances at any meaningful fraction of light speed requires energy inputs that scale exponentially and may exceed stellar output. The journey itself takes millennia to hundreds of millennia, during which the sending civilization must persist, the vessel must survive, and the destination civilization must remain in existence and detectable. The habitable windows of the relevant stars must overlap. The technological windows of both civilizations must overlap within those habitable windows. The overlap must exceed the journey duration, and the destination star's position must be predicted with sufficient accuracy across the full travel time. Each constraint is independent. Each carries its own probability of failure. Multiplied together, they produce a compound probability of successful physical contact that dwindles toward the infinitesimal. This is what temporal isolation means. The galaxy is not just too large, it is too old and too brief at the same time. Too old because its 13 billion year history dilutes any civilization's presence to a momentary flicker. Too brief because each civilization's window of existence passes before the slow machinery of interstellar travel can carry anything across the separating void. Two civilizations might both arise in the Milky Way across its long history. They might both develop technology, both look outward, both dream of contact. But if one burns brightly 6 billion years ago and the other ignites today, they are as separated as if they existed in different universes. The galaxy carried one to its grave long before the other opened its eyes. They occupied the same building. They never shared the same moment. The universe builds life repeatedly, perhaps abundantly, across billions of years, but it grants each experiment in intelligence only a sliver of time in which to reach outward. Most of those slivers pass in isolation, unable to find another sliver burning at the same moment within reach. The ships sail the same ocean. They sail it in different centuries, and the ocean does not care. But even if two civilizations beat every odd discussed so far, even if they arise close enough in space, overlap long enough in time, and command sufficient energy to attempt the crossing, one final barrier awaits. It is not a barrier of distance, energy, or time. It is a barrier of geometry, built into the expanding fabric of the cosmos itself. And unlike the others, it does not merely make contact improbable. For the overwhelming majority of the universe, it makes contact physically impossible, now and forever. Every barrier discussed so far, the crushing distances, the relativistic speed ceiling, the exponential energy costs, the merciless brevity of civilizational lifespans, operates within a universe that is at least standing still. The void between two stars may be immense, but at least it is a fixed immensity. A civilization contemplating a journey of 5,000 light years can plan around a destination that stays where it is. The gap is daunting, but stable. The target does not move away while you are trying to reach it. Except it does. The universe is not standing still. It is expanding, and it is expanding faster every year. In 1929, Edwin Hubble published observations confirming that distant galaxies are receding from us, and that the farther away a galaxy sits, the faster it retreats. This was not the motion of objects flying apart through a static space. It was the stretching of space itself, the fabric of the cosmos physically expanding, carrying galaxies along like specks embedded in a balloon that is being inflated. The galaxies are not racing away from us through the universe. The universe between us and the galaxies is growing. Hubble's law quantifies this expansion through an elegant linear relationship. A galaxy twice as far away recedes twice as fast. 3 times the distance, 3 times the recession velocity. The constant of proportionality, called the Hubble constant, currently measures approximately 70 kilometers per second per megaparsec. For every megaparsec of distance, roughly 3.26 million light-years, the recession velocity increases by 70 kilometers per second. At modest distances, this effect is negligible. The Andromeda galaxy, 2.5 million light-years away, is actually falling toward us under mutual gravitational attraction. Its inward velocity more than overcoming the expansion of the intervening space. But at distances of hundreds of millions of light-years and beyond, expansion dominates. Galaxies recede at thousands of kilometers per second. The most distant objects we can observe are racing away at velocities approaching and exceeding the speed of light. That last sentence deserves a pause. Objects receding faster than light. This appears to violate Einstein's cosmic speed limit. It does not. Special relativity prohibits objects from moving through space faster than light, but it places no restriction on how fast space itself can expand. The galaxies beyond a certain distance are not moving through space at superluminal velocities. They are stationary within their local region of space. But the space between them and us is accumulating so rapidly that the total separation increases faster than light could ever cross it. The distinction is subtle but physically precise, and its consequences are absolute. At a distance of approximately 14 billion light-years, the recession velocity equals the speed of light. This boundary is called the Hubble radius, and it marks a critical threshold. Beyond this distance, space expands faster than photons can traverse it. A light signal emitted from a galaxy beyond the Hubble radius, aimed directly at Earth, will never arrive. Not because the signal is too faint, not because something blocks it, but because the space the photon must cross is growing faster than the photon can cover it. The signal falls behind, like a swimmer stroking against a current stronger than any stroke can overcome. It moves forward through local space at the full speed of light, and yet it falls farther behind with every passing second because the total distance keeps increasing faster than the signal can close it. This is not a technological limitation. There is no hypothetical amplifier, no relay station, no ingenious encoding scheme that can circumvent this barrier. It is a geometric property of expanding spacetime. The photon is traveling at the maximum speed permitted by physics. The space is expanding at a rate determined by the energy content of the universe. When the latter exceeds the former, no causal connection is possible. No signal, no ship, no force of any kind can bridge the gap. The two regions become what physicists call causally disconnected. They exist in the same universe, governed by the same laws, but they can never interact, never communicate, never influence each other in any way. For the remainder of cosmic time, the observable universe, the sphere of space from which light has had time to reach Earth since the cosmos became transparent 13.8 billion years ago, currently measures approximately 93 billion light-years in diameter. This number exceeds the age of the universe multiplied by the speed of light, because space has been expanding throughout the entire journey time. Objects that emitted light toward us billions of years ago were much closer then. The light has been travelling ever since, but the expansion of space has carried those objects to distances far exceeding what light travel time alone would suggest. The cosmic microwave background radiation, the oldest light we can detect, was emitted from matter that was roughly 42 million light-years away at the time of emission. That same matter now lies 46.5 billion light-years away, carried outward by 13.8 billion years of cosmic expansion. Within this observable sphere sit approximately 2 trillion galaxies, each containing billions of stars. But this vast collection represents only what we can see. The total universe extends far beyond the observable volume. Measurements of the spatial curvature of the cosmos indicate that space is flat to extraordinary precision, which implies that the universe extends far past our observational horizon. Conservative estimates based on this flatness suggest the total universe measures at least 250 times the diameter of the observable sphere. The region we can access, the fraction of reality from which light has had time to reach us, may constitute less than 1% of what actually exists, and the situation is worsening. For decades, cosmologists assumed that the expansion of the universe was slowing down. Gravity, the mutual attraction between all matter, should act as a cosmic brake, gradually decelerating the expansion even if it could never fully halt it. In 1998, two independent research teams studying distant Type Ia supernovae discovered the opposite. The expansion is not decelerating, it is accelerating. Space is stretching faster with every passing era, driven by a pervasive, poorly understood component of the cosmos called dark energy. Dark energy constitutes approximately 68% of the total energy content of the universe. It permeates all of space with a constant energy density that does not dilute as the cosmos expands. Normal matter and radiation become less dense as space grows, because their fixed quantity spreads across increasing volume. Dark energy does not thin out. Its density remains constant per unit volume, which means that as new space is created by expansion, new dark energy fills it automatically. The more space exists, the more dark energy exists, and the stronger the repulsive effect becomes. Expansion creates space. Space contains dark energy. Dark energy accelerates expansion. Expansion creates more space. The cycle feeds itself without limit. This accelerating expansion has a consequence that may be the most profound and least appreciated fact in all of cosmology. The cosmic event horizon is shrinking. Not the observable universe, which continues to grow as ancient light reaches us for the first time, but the event horizon, the boundary beyond which events occurring right now will never be observable to us. Because expansion is accelerating, galaxies that are currently within our observable volume are being carried across this event horizon at an increasing rate. Once a galaxy crosses the event horizon, no event occurring there, no signal emitted, no light produced, will ever reach us. The galaxy does not vanish in a flash. Its light redshifts gradually, stretching to longer and longer wavelengths, dimming asymptotically toward invisibility. But the outcome is the same. The galaxy is gone, not destroyed, not hidden, simply removed from the realm of possible interaction, permanently and irreversibly. To grasp what this means for civilizations at different distances, walk through the expansion step by step, scale by scale, watching the prison walls close in. At a separation of 50 million light-years, roughly the distance to the Virgo cluster, expansion adds a recession velocity of approximately 1,100 kilometers per second. This is significant but modest compared to the speed of light. A signal sent from a civilization in the Virgo cluster would still reach us, delayed by 50 million years of light travel time, plus a modest additional stretch from expansion during the journey. Physical travel is another matter entirely. A vessel moving at 10% of c would take 500 million years to cross this gap, during which expansion would have increased the distance by a further several percent. The destination recedes while you chase it. At 10% of light speed, you are faster than the recession velocity at this distance, so you eventually arrive. But the journey takes longer than the naive distance divided by velocity calculation suggests because you are running on a treadmill that stretches beneath your feet with every stride. At 500 million light-years, the recession velocity has climbed to roughly 10,800 kilometers per second, approximately 3.6% of the speed of light. A vessel traveling at 10% of c can still outrun the expansion at this distance, but barely. The journey time extends dramatically beyond the straight-line calculation because the ship must continuously overcome the growing gap. At 5% of c, the vessel can no longer gain ground. The space it has yet to cross expands faster than it can traverse at that speed. The destination pulls away forever. For any civilization limited to 5% of C or below, 500 million light-years represents an absolute and permanent wall. Nothing they build, no matter how durable, will ever arrive. At 1 billion light-years, the recession velocity approaches 21,600 kilometers per second, roughly 7% of c. A vessel must exceed 7% of the speed of light merely to avoid falling behind. It must exceed this speed substantially to make meaningful headway. At 10% of c, the effective crossing speed is only 3% of c after accounting for expansion, turning a nominal 1 billion light-year journey into a voyage lasting tens of billions of years. By the time the vessel arrives, the star it was aiming for may have exhausted its fuel and collapsed into a white dwarf or neutron star. The planet may have been swallowed by its star's red giant phase billions of years earlier. The travelers would not merely arrive too late for the civilization, they would arrive too late for the star. At 5 billion light-years, the recession velocity reaches roughly 36% of the speed of light. Only a vessel capable of sustained travel above 36% of c can even begin to close the gap. Achieving 30% of c requires energy equivalent to years of total human energy output for a 1,000-ton payload. Exceeding 36% pushes the requirement higher still. The civilization attempting this journey must command energy resources surpassing anything but the complete harnessing of a star, maintained not for the duration of an acceleration burn, but for a voyage lasting billions of years, during which the vessel must continuously fight the expansion of the space it is crossing. The engineering is not merely difficult, it is physically incoherent. No vessel can carry enough fuel to sustain propulsion for billions of years. No external energy source can track and power a vessel across such distances. The journey is not impractical. It is impossible under any known physics. And beyond roughly 14 billion light-years, the question becomes moot. The recession velocity exceeds the speed of light. The expansion has imposed a permanent verdict. Those civilizations are severed from our causal future as completely as if they existed in a separate universe. They could launch an armada at 99.9% of c, and every ship would fall further behind with each passing second. They could be broadcasting at maximum power in every direction, and we would never receive a single photon. The expanding universe has placed an impenetrable wall between us, a wall that grows thicker with every passing second and will never be breached. Currently, roughly 97% of the galaxies within our observable volume are already receding faster than light. We can see them only because their light began its journey when they were closer, before expansion carried them beyond the critical threshold. We are looking at their past. Their present is already unreachable. Their future belongs to a realm we can never touch or influence. Every photograph of the deep universe is a portrait of objects we can observe but never touch. Within the gravitationally bound local group, roughly 80 galaxies, including the Milky Way and Andromeda, expansion does not dominate. Gravity holds these galaxies together. The space between them is not stretching fast enough to overcome their mutual attraction. The Milky Way and Andromeda are approaching each other at roughly 110 kilometers per second and will merge in approximately 4 to 5 billion years. The local group is an island of gravitational coherence in an ocean of accelerating expansion. But beyond the local group, every structure is receding, and the timeline of loss is not abstract. It follows a specific, calculable schedule that astronomers can project with confidence based on current measurements of the Hubble constant and the dark energy density. The Virgo cluster, 54 million light-years away and the nearest major concentration of galaxies, will cross the cosmic event horizon within approximately 100 billion years. Its galaxies, its thousands of stellar furnaces, its possible civilizations will redshift beyond detection and pass permanently out of causal contact. Any civilization in the Virgo cluster that we have not contacted by then becomes unreachable for eternity. Not for a long time, for eternity. The Coma cluster, roughly 320 million light-years distant, crosses the horizon sooner. Its higher recession velocity carries it beyond causal reach within approximately 80 billion years. The great walls and filaments of the cosmic web, the largest structures in the observable universe, will fragment and dissolve from our causal volume over similar timescales. Each structure that crosses the event horizon is not merely lost to observation, it is lost to interaction. It can never again affect or be affected by anything. In our local group, within approximately 150 billion years, every galaxy outside the local group will have crossed beyond the cosmic event horizon. Future observers in the merged remnant of the Milky Way and Andromeda will inhabit a cosmos that appears to contain a single galaxy surrounded by perfect, infinite emptiness. The cosmic microwave background will have redshifted to wavelengths so long that no conceivable instrument could detect it. There will be no observational evidence that other galaxies ever existed. No evidence that the Big Bang occurred. No evidence that the universe was ever anything other than a single galaxy floating in a static, eternal void. This is not a distant hypothetical disconnected from the question of civilizational contact. It is directly relevant because it establishes an absolute upper boundary on which civilizations can ever interact. Any two civilizations residing in separate gravitationally bound structures in different galaxy groups or clusters face a hard deadline imposed by cosmic expansion. If they do not establish contact before expansion carries them beyond mutual causal reach, they never will. The deadline is not negotiable. It is not contingent on technological advancement. It is a consequence of the geometry of space-time under accelerating expansion, and no technology operating within the laws of physics can circumvent it. For civilizations in separate galaxies, this deadline may already have passed. A civilization in a galaxy currently receding from us at faster than the speed of light is already beyond reach. No vessel we launch today, at any speed up to and including c, will ever arrive there. The space to be crossed is growing faster than any ship can traverse it. A civilization in such a galaxy might be brilliant, ancient, desperate for contact, broadcasting signals in every direction, and it does not matter. The expanding universe has placed an impenetrable wall between us, a wall that grows thicker with every passing second and will never be breached. Within the Milky Way itself, cosmic expansion is not the dominant factor separating civilizations. Gravitational binding holds the galaxy together. The distances within our galaxy, measured in thousands of light years, are not increasing due to expansion. The barriers within our galaxy remain the speed limit, the energy abyss, and the cruel brevity of civilizational lifespans. But expansion eliminates the possibility of assistance or rescue from beyond the galaxy. If the answer to the Fermi paradox lies in some other galaxy, if a civilization somewhere in the Virgo cluster or the Coma supercluster has solved the problems of interstellar travel within their own galaxy, they cannot help us. They cannot reach us. The expanding universe ensures that intergalactic travel is not merely difficult. For the vast majority of galaxy-to-galaxy combinations, it is physically impossible. Now assemble the full architecture of isolation, every barrier layered upon every other, and observe the cumulative structure, not quickly, slowly, because the weight of this argument depends on understanding that these are not different descriptions of the same problem. They are 6 independent problems arising from 6 different branches of physics, each one sufficient on its own to make interstellar contact extraordinarily difficult, and together forming a compounded barrier whose total strength exceeds the sum of its parts. Layer 1. Civilizations, even if common, are separated by thousands to tens of thousands of light years within a single galaxy. This is a consequence of stellar density and galactic volume, imposed by the geometry of a disk 100,000 light years wide, containing 400 billion stars. This barrier arises from astrophysics and spatial statistics. It cannot be reduced by any technology. It is a fact about how matter distributes itself within galaxies. Layer 2. The speed of light is an absolute ceiling on the velocity of any massive object. This is a consequence of the structure of space-time as described by special relativity. a framework so deeply embedded in modern physics that no serious theoretical challenge to it has survived experimental scrutiny in over a century. This barrier arises from fundamental physics. It has been tested to more decimal places than any other physical law. It is not subject to revision by future engineering. Layer 3. The energy required to approach light speed scales exponentially with velocity, compounded by the rocket equations demand that fuel mass grows faster than payload mass. Even the most efficient theoretically conceivable propulsion systems require stellar-scale energy inputs to accelerate meaningful payloads to a significant fraction of c. This barrier arises from thermodynamics and the mathematics of momentum conservation. It applies to every propulsion system that obeys the laws of physics, which is all of them. Layer 4. Technological civilizations exist for brief intervals relative to galactic time. Even granting million-year lifespans, the probability that two civilizations coexist within overlapping temporal windows and within travel range of each other is small. The journey times required to cross the separating distances frequently exceed the lifespans of the civilizations attempting them. This barrier arises from biology, ecology, and the statistics of existential risk. It is independent of physics and would constrain contact even if faster travel were possible. Layer 5. Stars have finite habitable windows determined by their mass and evolutionary stage. Civilizations arising around different stellar types experience habitable windows that may not overlap. A civilization that thrived 7 billion years ago left no destination for a civilization arising today. A civilization that will emerge 3 billion years hence offers no target for a civilization that exists now. This barrier arises from stellar astrophysics and the nuclear physics of hydrogen fusion. It operates on timescales of billions of years and determines which stars can support life and for how long. Layer 6. The universe is expanding, and the expansion is accelerating. Beyond the local gravitationally bound group, every galaxy is receding. Most of the observable universe is already causally disconnected from us. Intergalactic travel is physically impossible for the overwhelming majority of galaxy pairings. Even within the observable universe, the window for intergalactic contact is closing and will eventually shut permanently. This barrier arises from general relativity and observational cosmology. It is the most absolute of the six because it imposes not merely difficulty, but impossibility across the largest scales. Each of these layers operates independently. Each arises from a different branch of physics. They are not different facets of a single obstacle. They are 6 separate walls nested inside each other, each one catching anything that slips through the wall before it. A civilization that solves the energy problem still faces the speed limit. A civilization that achieves high velocity still faces the temporal mismatch. A civilization that happens to coexist with a neighbor still faces the distance. A civilization that exists in another galaxy faces expansion. The barriers do not compete with each other. They collaborate, each one covering the gaps left by the others, forming a prison with no single point of failure. Multiply the probabilities. Even using the most generous assumptions at every stage, the compound probability of 2 independently arising civilizations physically meeting each other drops to a figure so small that it functionally rounds to 0. Not exactly 0. Physics does not forbid a civilization from launching a vessel at 1% of c toward a destination star and arriving 100,000 years later to find another civilization in its technological prime, ready and willing to make contact. It is permitted, but the probability that all necessary conditions are satisfied simultaneously, spatial proximity, temporal overlap, sufficient energy, survivable journey, persistent destination, is so low that across the entire history of a galaxy the size of ours, it may never happen once. This is the resolution the universe offers to the apparent paradox of cosmic silence. The question is not, where is everybody? The question is malformed. It assumes that the existence of other civilizations implies the accessibility of other civilizations. Physics makes no such guarantee. The universe may be saturated with intelligent life, thousands of civilizations burning across the Milky Way's history, millions scattered across the 2 trillion galaxies of the observable universe. And yet the architecture of the cosmos, the distances, the speed limits, the energy barriers, the temporal mismatches, the stellar deadlines, and the relentless expansion ensures that virtually none of them will ever physically encounter another. The silence is not evidence of absence. It is evidence of structure. The universe is built to produce life in isolation, not by malice, not by design, simply by the operation of the same physical laws that allow stars to burn, planets to form, and chemistry to become biology. The laws that create life also create the prison. The same relativity that governs the nuclear reactions powering stars also limits the speed at which anything can travel between them. The same gravity that pulls gas clouds into stellar nurseries also determines that galaxies spread across millions of light years of void. The same dark energy that accelerates the cosmic expansion also ensures that most of the universe is permanently beyond reach. Creation and isolation emerge from the same equations. There is a temptation to receive this as tragedy, to feel the weight of cosmic loneliness pressing down, the knowledge that however many civilizations have gazed at alien skies and wondered, they are almost certainly doing so alone. The vessels never launched, the signals never received, the handshake across the void never completed. 2 intelligences, each burning with curiosity and longing, separated by a gulf that neither can cross. But there is another way to hold this knowledge. Consider what the universe has accomplished. From an initial state of unimaginable density and temperature, it expanded, cooled, and organized itself into structures of staggering complexity. It built atoms from subatomic particles. It forged those atoms into stars. It cooked heavy elements in stellar cores and scattered them across light years in supernovae. It gathered those elements into planets, stirred them with energy, and waited. In at least one case, and probably in billions of cases, the waiting paid off. Chemistry became biology. Biology became complexity. Complexity became awareness. Awareness. The universe produced matter that can contemplate itself. Atoms that can wonder about atoms. Stardust that can study the stars it came from. Whatever your view of consciousness and its significance, the emergence of minds capable of understanding the cosmos they inhabit is a phenomenon of extraordinary rarity and extraordinary consequence. The universe spent 13.8 billion years building the conditions for this moment, the moment in which a configuration of matter looks outward and grasps, however imperfectly, the true scale of what exists. That understanding is not diminished by isolation, it is sharpened by it, precisely because we cannot meet the other minds that may exist across the cosmos. Our understanding of the cosmos itself becomes more precious. Every equation derived, every observation recorded, every theory tested, represents a civilization reaching as far as its confinement allows. The walls are real, the reaching is also real. And there is something magnificent about a species that reaches even when it knows the walls are there. The structure of the universe is not a flaw, it is an architecture. The same expansion that isolates civilizations from each other also cooled the primordial plasma into atoms, allowing chemistry to begin. The same distances that prevent contact also prevent a single catastrophe from sterilizing an entire galaxy. The same stellar lifetimes that create temporal mismatches also provide the billions of years of stable energy output that life requires to evolve. Isolation is not the cost of a poorly built universe. It is a feature of a universe built precisely right for the emergence of complexity and awareness, distributed across scales that ensure no single event can extinguish all of it simultaneously. Look up tonight. Every point of light in the sky is a sun. Many of those suns warm worlds. Some of those worlds may harbour oceans, atmospheres, ecosystems, civilizations. The photons arriving at your eyes have travelled years, decades, centuries, carrying information about places you will never visit and beings you will never meet. The light connects you to them. The space separates you from them. Both the light and the space are governed by the same physics, emerging from the same fundamental constants, expressed through the same mathematical structures that have operated without interruption since the first fraction of the first second after the cosmos began. The universe is not empty, it is full of stars, full of worlds, full of potential, full of the same chemistry and the same physical laws that produced you. And it is full of distance. Magnificent, terrible, humbling distance. Distance that exists not as a punishment, but as a natural consequence of a cosmos large enough, old enough, and structured precisely enough to produce minds capable of measuring it. Somewhere, separated from you by thousands of light years of vacuum, another mind may be reaching the same conclusion tonight. Sitting beneath an alien sky, surrounded by unfamiliar constellations, understanding for the first time that the universe creates life and then keeps it apart, not out of cruelty, not out of indifference, out of geometry, out of physics, out of the deep mathematical structure that makes stars and planets and minds possible in the first place. You will never meet them, they will never meet you, but you share something no distance can erase. You share the same universe, the same laws built you both. The same stellar furnaces forged the calcium in their bones and the iron in your blood. The same cosmic expansion that isolates you from each other also gave both of you the time and space to exist. That is not loneliness. That is belonging to something so vast that no single part of it can see the whole. Every civilization is a window. Every window looks out on the same cosmos. And the cosmos is extraordinary enough to be worth the view, even if the only eyes that ever see it through your particular window are your own. The universe was not built for meetings, it was built for wonder, and in that purpose, it has succeeded beyond any measure a small mind on a small world could ever fully grasp.